Hi everyone, my name is Amira Darwish. I'll be explaining my work for Project 2 in the Megatronics class under Dr. Yasser Ismail. The project involves calculating the rotation matrices for each joint of a 6DOF manipulator and determining the final rotation matrix for the end effector using Python. I'll walk through the code, explain the math behind it, and show the results. To begin this project, you need to download Python, which is what I'm showing you on the screen right now. Make sure to choose a version that is compatible with the version of NumPy you'll be installing later. I recommend using the latest version. After that, you can go ahead and download NumPy. Before installing NumPy, double check that the version of NumPy you're downloading is supported by the Python version you installed. After downloading NumPy as a zip file, you need to take a few extra steps to make it work with Python. After downloading NumPy, first unzip the downloaded file. You're going to go ahead and find this file, and then you're going to copy it. And you're going to navigate through your Python installation dictionary, which I have it right here. You're going to go to the library. Then you are going to find site packages. And after that, you are going to paste the file you copied for NumPy, and it's going to look something like this. Once I've pasted NumPy files into the Python library, I'm going to test if NumPy works properly. To do that, you'll have to open idle. I already have it open as a new untitled doc, and I'm going to type in import NumPy as NP, and I'll press enter. As you can see, it did not show me any errors, so this means NumPy has been installed correctly and is ready to be used. Now I'll go ahead and explain the code I used for this project. First, I import NumPy by using the command import NumPy as NP. This allows me to use all of the NumPy functions in my code, which are crucial for handling matrix operations, like calculating the rotation matrices for each joint of the robotic manipulator. After that, we can go ahead and continue with our code. Joint angles initialization. Here we initialize the angles of each joint T1 to T6 in degrees. Each variable represents the rotation angle of a corresponding joint in the 6DOF manipulator. After that, we are going to go ahead and convert to radians. Each angle is converted from degrees to radians. This conversion is necessary because the trigonometric functions in Python's NumPy library use radians. The formula used is radians equal degrees over 180 times pi. I'm going to show you the code for the rotation matrix. Rotation matrix R01, the matrix represents the rotation of the first joint about the y-axis. The matrix is constructed using the cosine and sine of the angle T1, reflecting the rotation behavior in 3D space. And this is what's happening in R01. In R12, this matrix represents the rotation of the second joint, also about the y-axis. The negative sign of T2 is used to adjust the direction of the rotation. In R23, this is the identity matrix, and indicating that there is no rotation for the third joint. It serves as a placeholder in the kinematic chain. Sorry. Rotation R3, 4. This matrix represents the rotation of the fourth joint. It involves a rotation about the y-axis, reflecting the relationship between the joints. R4, 5. Similar to the previous ones, this matrix represents the rotation of the fifth joint about the y-axis. Rotation matrix R5, 6. This matrix represents the rotation of the sixth joint, but about the z-axis. It combines sine and cosine to reflect the rotation correctly. The next step in our code combines and calculates. Right here we are combining R01 and R12. This line calculates the rotation matrix from frame 0 to frame 2 by multiplying the first two rotation matrices. The np ... function performs matrix multiplication. Right here, combining R23 and R34, we combine the identity matrix for the third joint with the rotation matrix for the fourth joint, resulting in the rotation matrix from frame 2 to frame 4. Combining R45 and R56, this line combines the matrices for the fifth and sixth joint to find the rotation from frame 4 to frame 6. And right here, combining to R04, this calculates the rotation matrix from frame 0 to frame 4 by multiplying the previous results. Final rotation matrix R06. Finally, this line combines all the matrices to determine the overall rotation of the end effector, which is frame 6, with respect to the base frame, which is frame 0. Moving on to our last part of the code. Which is printing. So what's happening right here, as you can see, printing R01. This line begins by printing the label R01, indicating that the output following this line will display the rotation matrix from frame 0 to frame 1. The np.matrix R01 converts the rotation matrix R01 into a matrix format that is easier to read. Using print allows the user to see the specific rotation that occurs due to the first joint's angle T1. And we are doing the same thing for all the others. Now for the last part of our project, we are going to run the code. All right, as you can see, the code is successfully working. And now we need to ensure that the end results is correct. If the output does not match our expected results, it indicates that there may be an error in the code. Next, we'll modify the angles in the code to see how changing the degrees affects the rotation matrices and final position of the end effector. Right, we can go ahead. All right, we're gonna come up here. We'll change T1 to 90 degrees. And we'll do the same with T4. Right, and we'll run it. Save. All right, so now it's showing us the new results after changing R01 and R34 to 90 degrees, and the effector always changed since all of them are summed up and added in the last one, R06. The code is successfully working, and this will be the end of my video. Thank y'all so much for listening. Have a great day.